Yes, thank you. And let me introduce you. And today, the type of the second talk is on particle filters and the particle fluid filters, and smooth towards fully nonlinear data assimilations. And it's our pleasure to have the Professor Peter Jovan Duven here today. And his research is focused on the use of data assimilation and causality influence for better understanding geophysical fluid with emphasis on the atmosphere and ocean. This includes further development of data assimilation methodology for highly nonlinear high-dimensional geophysical systems of causality theory for these systems. He also has a research group at the University of Reading working on these two projects, data assimilation in high nonlinear systems and causality relationship using nonlinear data simulations. He is a professor in data assimilation and physical oceanography, Colorado State University in US, and professor in data assimilation, University of Reading. He was director of the Data Assimilation Research Center from 2009 to the 2019, director data simulation research from 2014 to the 2018, director National Center for Earth Observations from 2013 to 2014. And thank you very much for coming to here today, and please go ahead.
So thank you so much, Wenjing, and also Haroldo to invite me to this short course. It's very well, it's a privilege to be here, and then I'm keen to talk about some of the things that are close to my heart, which is the nonlinear data simulation. And so the way I want to do this is so when I present my screen, I cannot see this chat. So, and of course, if you have a question in the beginning, you might have to wait for an hour to get an answer. That's perhaps not really working. So I would actually suggest that if you have a pressing question, just speak up. I can't see the chat, like I said. So just raise your voice, and I'll stop and try to answer it. And of course, when there are too many questions, I'll have to moderate this in a different way. But let's start out this way and see how that works. So, so my motivation is, my basic motivation is try to understand geophysical fluids like the ocean and the atmosphere, and the sea ice and the sun, and well, you name it. And of course, we have two sources of information: observations and we have models. And they both contain an enormous amount of information that we want to combine using data simulation. So that's where my interest for data simulation comes from. And let me see, I can't do that. And yeah, I will talk specifically about particle filters and particle flows here. So you probably have heard of particle filters. Particle flows are the new child in the block, and I think they're quite interesting. Okay, so that's not going to work. This is okay. So before I start, so this talk has three parts. The first one is a small part on probability density functions, just to refresh your memory, I guess. And then I talk about particle filters, and then about the flows. So first of all, suppose we have a probability density. So we have in this. Can you see my my cursor? Is that visible?
Yes, we can see. Yeah,
okay,
yes,
great.
we can see.
Fantastic. So if you look at this picture on the upper left, the horizontal axis would be the let me just do this. The horizontal axis is a variable, let's say the temperature in Rio de Janeiro, and the vertical axis is the probability density. And the, have I missed one slide? Yes, I've missed one slide, sorry. And so this probability density tells us how the probability of a certain event is distributed over the different values of the temperature. So suppose what we want to know, what's the probability that the temperature in Rio tomorrow at noon is between 30 and 32 degrees Celsius. So what we have to do then, if we have to integrate this green area here, this green area, this hashed green area gives us the probability that it happens. So we integrate, if we go to the right, from Z1, which would be 30 degrees Celsius, to Z2, which would be 32, and then we integrate over the PDF. Actually, I don't know what the temperature in Rio is. I just realized this, of course, it's winter. So maybe this is better for Reading, actually, or Oxford. These probabilities are quite high these days. But that's how you use the probability density. It's related to the probability by just integrating over your area of interest. Now, if we go further with probability density, of course, when I want to know what is the probability that the temperature in well, let's say Imperial in London is between absolute minimum, so what is it, minus 273.15 Celsius, and let's say 1,000,000 degrees Celsius. But that probability, of course, that is in that range, within that range, that probability is 1. We know that the temperature will be in that range. And so the probability density has to be normalized to 1. And so if I integrate over all possible values of Z, I get the number 1. And we can define the expected value, or the mean, as I just multiply the PDF with the variable of interest, G, and then integrate over all the possible values, and then I get the mean, and I can of course calculate the mean of a function of the variable. Suppose the variables in well, let's say in my model I have horizontal velocities u and v, and I want to know the speed of the wind, the horizontal speed of the wind. Now that's of course a nonlinear function of the velocities. It's u squared plus v squared, and then the square root of that whole thing. If I want to know the mean of the wind speed, and I have the PDF of u and v, then this function g would be a nonlinear function of u and v, but I can still just calculate the mean with this equation over here. And I can calculate higher order moments, like the variance, which is a measure of the uncertainty, of the width of the PDF, etc., etc. And of course, we don't have just one variable. Right? If you think about the atmosphere for numerical weather forecasting, we now run these models with, what is it nowadays? It's I think it's 10 billion variables, something like that, 10 to the power 10, maybe 100 billion. I don't know, but it's huge. It's number of variables is huge. I don't know how to display that many variables, so let's do two. So here on the left-hand side, I have the joint PDF of two variables x and y. That could be the temperature in London and the temperature in Rio. And it's the joint PDF. So it's again the distribution of the probability of certain events, temperature events in this case, in London and Rio. Now from this joint PDF, I can calculate the temperature distribution in Rio. Right? So what I do, I just integrate out all the possible temperature values in London, and then so I just integrate along all these horizontal lines, and then I get this P of y here, sorry, PDF of y, the probability density of the temperature in Rio, and I can do the same for London, right? So this joint PDF is a very powerful thing to have. There's a lot of information in there. It gives us how the probability density of the temperatures in these two different cities are connected to each other. But it also gives us just the temperature distribution in London and the temperature distribution in Rio. Now in data simulation, we need something else. We need a so-called conditional PDF. And if we go to the right-hand side of the figure, we see, for instance, the PDF of y given x. yeah, that's something that shows up in the basic in Bayes' theorem, the basic equation for data simulation. Now, so what is this? If we again look at the picture on the left, the joint PDF, then suppose I know that that x is equal to 1. So x is equal to 1, and I want to know what is the probability density, of y. So what I have to do is I have to look at what the PDF is along this line here, along the line x is 1, along this vertical line. And you see, oh, but that's just the value of the joint PDF along that line. Apologies again. The value of the joint PDF along that line. So yeah, that makes sense. So that's what we have. But there's one small caveat, and it is that, of course, when I look at the PDF along this line, it doesn't integrate to 1. So if I integrate over all the y values, it's not equal to 1. So it's not a properly normalized probability density function. So I have to normalize it. And how do I do that? Well, I just divide by the integral of the PDF along this line. And what's the integral of the PDF along this line, along x line? That is PDF of x. And so this conditional PDF is nothing magic. It's just a joint PDF evaluated along a certain line and then normalized by the total probability mass along that line. Now, like I said, we're going to use that a lot. But before we do that, it's important to realize that there are two ways to represent these probability densities. And the way you're most used to, I guess, is so-called parametric representation. So you know a few moments of the PDF, and then that's enough to define the PDF. For instance, for a Gaussian PDF or normally distributed variables, as like over here, then we need the mean, mu, and the standard deviation, sigma. And as soon as I know these two, I know everything there is to know about this PDF. I can calculate everything that I want from these two moments. So these two parameters define the whole PDF. And the other example here, exponential, gamma, etc. There's an enormous amount of standard PDFs. But sometimes the PDFs do not have a specific shape. The shape can be anything. It can be well, it can be anything, not a standard PDF. And how do we represent the PDF then? Well, the way we can do that is by samples. And this is very much like an ensemble common filter. You're used to this. We have an ensemble of states, of model states, and they represent the probability density function. Now, in the ensemble common filter, remember that we are only interested in the mean and the covariance. So we only need to calculate the first two moments of the PDF from the ensemble mean and the ensemble covariance. But if we do nonlinear data simulation, the PDFs can, like I said, have very different shape, and the Gaussian shape might not be very good. So we need to do something else. And so what we can do is a more general way. We can write the PDF in as this equation over here. So it's similar or the same as an ensemble common filter in a sense. And we have our ensemble members Z and E, and we represent the PDF by the sum of delta functions. And we have NE, so let's say 50 ensemble members. So this is the mathematical description of my PDF in terms of an ensemble of model states. So that contains these delta functions. So let's have a look at these delta functions, because they're they're actually really important in the whole story, in nonlinear data simulation in general, and all the sample methods that do not assume Gaussian structures. So like I said, the PDF can be represented, can be written as in this way, the sum of delta function. Now what's a delta function? Well, first of all, it's not a function. It's actually a distribution, but that's a mathematical nicety. Yeah, but we can see it as sort of as a function that is zero everywhere, except and when z, the variable is not equal to z star, then the delta function is zero. And everything that I multiply with that delta function in these places where the delta function zero will become zero. But funny enough, when z is equal to z star, then this delta function is infinitely large. And you can understand that's sort of not a real function. But infinity is well defined in the sense that if I integrate the delta function from minus infinity to plus infinity, so over all possible values of z, then I get exactly 1. So in that sense, it's actually a possible probability density function. But again, it's not a function. So why we like it so much is this last line, the last figure, the last equation on this page. If I have a function g of z, and I multiply that with the delta function, so that looks a bit complicated, but then if we integrate over the whole domain, then what the delta function does, and remember the delta function is zero when z is not equal to z star. So it will kill all values of z where, of g of z, sorry, all the g of z's when z is not equal to z star. And the only place where it's non-zero is when z equal to z star. So you can sort of imagine that if I do this integral, then I get the g of z star out. And so if I have complicated integrals, as soon as I have delta functions within those integrals, I can actually do the integral and I get very quickly get what I want. And this equation here is the definition of the delta distribution. But that's a detail. So with that, we are going to take 1 minute rest, perhaps. And then we go back to data simulation. So the first part is done. I see there are questions in the chat. Should I? I think they're all okay.
No, up to now, we don't have any questions in the chat.
So, if someone has any questions about probability density functions, then please go ahead now. But if not, then I'm going to try to at least move on. Yeah, here we are. So, as you will have realized, the fundamental basis of data simulation is Bayes' theorem. Every data simulation method that you've ever heard of can be derived from Bayes' theorem, either directly or you start with Bayes' theorem and you make some approximations, and then in the end you get what you want. All the inverse methods, etc., they can all be derived from Bayes' theorem. Now, so it's extremely general, but it's also extremely powerful. Because it gives you the exact solution to any data simulation problem. We know, in a sense, we know what the solution to any data simulation problem is. The devil is in the details, right? We don't know exactly how to calculate the things, but we know how to do it in principle. So that's quite useful. But let's start. How do you read this equation? Well, you start on the right-hand side with P of x. So we start reading from right to left, not from left to right, but from right to left. We start with this P of x. That's the prior probability density, and the prior distribution of the state variable. And remember, the state variable is a model state, and it could be the model state for an atmospheric model. So that state vector would then have in that vector the temperature in all the grid points of the model, the pressure in all the grid points, the velocities, horizontal, vertical, etc., in all the grid points, humidity, cloud variables, etc. So it would be an enormous vector. And so indeed, think about this x as a huge vector, maybe of the order of a billion variables. And we need the probability density of that. So we need to know for each of these possible vectors, what is the probability density? So that we can calculate, probabilities of events. Anyway, this is what we have before we see the observation. So this is a starting point of the data simulation. this prior information that typically comes from a forecast. So we have a forecast that started yesterday, and it's we propagate the model to now. That was the forecast for yesterday, but now observations come in, so we're going to combine that forecast with the observations, and the observations are denoted by y in this equation. So y is the observation vector, and again, it's a huge vector. It can easily have 1 million or 100 million variables. Yeah, it's all huge for numerical weather prediction. So what we need is this conditional density of y given x. But it's a bit funny because y is given, right? Y is a set of observation that I know. So what is this probability density? There's no uncertainty in y, in the sense that, of course, there's observation errors, right? But there's no uncertainty in the values of y. I know what they are. I've made my observations. There's no uncertainty there. So this function here, this conditional PDF, is actually, you should see it as a function of x. Y is actually fixed, and x is the variable here, and so that's why this is called not a PDF, but typically it's called a likelihood. It's the likelihood of the state. So how likely it is for a certain state x to give the known observation vector y. That's what this likelihood is. And then we have this normalization factor, which turns out to be the marginal of the observation, marginal distribution of the observation. Turns out that for all the data simulations methods that we talk about in this course, I think, we don't need them. So we're not going to worry about them. The main point is you see that they don't depend on x. So indeed, they're not that interesting, and typically this normalization factor falls out. So that brings us to what is data simulation? Well, we take the prior, we just multiply it by the likelihood, and we get the posterior PDF. So that's the probability density of the state given the observations. And this is the solution to the data simulation problem. This is it. This is what we are after. Everything else is actually derived from this probability density function. For instance, if you look at the variational methods, that tries to find the mode, so a maximum of this posterior PDF. And we do that by minimizing the cost function. But it's trying to find the maximum of this thing. The common filter and ensemble common filters typically try to find the mean of this posterior PDF. But of course, you can be more general, right? You can say, well, for nonlinear data simulation, we're interested not only in the mode and the mean, we're interested in this distribution. So we're interested in this whole posterior PDF. Now the question is, how do we, okay, we've written down the solution to the data simulation problem, but what does all these things mean, and how do I get them? And that's where the problem is. So let's start with the prior. And let's start with the prior. So how do we get the prior? Well, like I said, the prior comes from the model forecast. So we have an atmospheric model, and we propagate it forward from yesterday to today, or from today to tomorrow. And we do that with the model equations. So this equation over here is my model equation. So x is my state vector. So the change in the state vector is due to a deterministic, my deterministic equations. So the Navier-Stokes equation, thermodynamics, the whole thing. And I have here, to make it general, I also have model errors here. So the d beta, excuse me, so beta is a Brownian motion, and no, that's perhaps a detail, but this is a random term that I add to the deterministic model to represent things in the model equations that are not perfect. And we know the model equations are not perfect, otherwise we wouldn't need any observations, which is run the model and we're done. But there are errors in the model equations, and we present that by the beta. And typically we assume that the model errors are Gaussian distributed, but we don't have to. But that's the typical assumption. Now, the beauty of mathematics is that sometimes it does very useful things. It gives us very useful things, and this is one of them. So if I have this model equation, mathematics gives us immediately an evolution equation for the probability density function. So this, the so-called Fokker-Planck equation or the Kolmogorov equation, is an evolution equation for the PDF of X, for the whole PDF, this whole thing. I still think it's amazing. Just give me the model equation of your model, and then I can write down in principle the evolution equation of the whole PDF of X.
Peter,
Yes.
This stochastic process is a Markovian one?
Yeah, so what I did here, I didn't specify it at all, of course, but the idea is here that there's no memory in the model error. But of course, you can include model error, and that's a higher order Markovian process if you want. Does that make sense?
Yeah.
Okay.
Thanks.
Okay. But indeed, the Fokker-Planck, these equations will become slightly more complicated if you do that. But they're still, you can still do this. So, and the F here, so if you look at the Fokker-Planck equation, this F here is the same as the F here, there, right? So we take the model equations and we use them to propagate the probability density in model space. And then we take the divergence of that. And we also see this term here, the second term on the right-hand side, that looks a bit like a diffusion term. And indeed, right, it is proportional to this Q, and Q is related to the model errors, so to these random terms. So clearly, if I have these random terms, then the uncertainty grows over time. So that Q here that acts in the same way as a diffusion coefficient. It makes the PDF wider and wider. We are less and less certain what happens. So we can actually understand this Fokker-Planck equation quite well, just from the standard advection diffusion equation. Anyway, so in principle, this is the way to bring the PDF that we had yesterday to today, and then that PDF can act as a prior in my data simulation. Now, that's all very nice, but this Fokker-Planck equation is a beast, right? It's an infinite dimensional equation. It's nice that it's linear. It's always linear in the probability density. If we go back, you see it's a linear equation in P, even if the model itself is highly nonlinear. The equation for P is linear. But we go from a finite dimensional nonlinear model to an infinite dimensional linear model. So maybe we didn't gain that much because it's infinite dimensional. How do we do this? So how do we do this in high dimensional system? Well, the trick is, again, we use an ensemble. We use an ensemble of model states. So we don't explicitly propagate the probability density forward in time, but we use the model equation for different model states, an ensemble of model states, and propagate that whole ensemble forward in time. And that ensemble will be, well, if the ensemble is large enough, then that ensemble will perfectly, well, not perfectly, will be a good approximation to this Fokker-Planck equation, to the evolution of the probability density function. So luckily, we don't have to solve this infinite dimensional problem. We can just use a whole set of ensemble members to solve the Fokker-Planck equation. So we know how to propagate the probability density forward. And actually, this is done by numerical weather prediction centers every day. They make an ensemble forecast, and that ensemble represents a PDF, a probability density function. So let's have a look now at the specific data simulation methods, because I said, well, we can write down Bayes' theorem, so we know the data simulation is the solution, but how do we do this in practice, right? I said, okay, I have my PDF, can have any shape, P of X here. So I represent it as a set of ensemble members, and I do that here with these delta functions. But how do I use it then in Bayes' theorem? And oh, by the way, you notice perhaps that the denominator looks different from what we had before. This is actually the same, and we can write P of Y, the marginal probability density of the observation also in this form. It doesn't really matter. It doesn't matter for the story, so I'm just pointing this out. Okay, so let's assume that we have this representation of the prior PDF, just a bunch of ensemble members. Now, what the particle filter does, and it's so super simple, it's embarrassingly simple. It's the simplest data simulation method you can imagine. It just takes this representation of the prior and plugs it in Bayes' theorem directly. And what I get, well, of course, these delta functions, they are 0 whenever x is not equal to one of these ensemble members. So that means that the likelihood will also be 0 unless x is equal to one of these ensemble members. So what I'm left with, if I plug this into there, I'm left with this expression over here. So I get the same delta functions, they're still there, but these w's now, these weights, are directly related to the likelihood. And you see here that it's y given xi, and xi is one of the ensemble members, and I sum over all the ensemble members. So yeah, you see sort of immediately that this has to come out. And you see that the weights are normalized such that the sum of all the weights excuse me, is equal to 1, which is yeah, it sort of happens automatically in this method. So what did the data simulation do? So we started with this ensemble, but excuse me, in the posterior we have the same ensemble members. So what happened? Well, the difference is that here we had this factor 1 over n, which is constant for every ensemble member. So this was an equal weight ensemble. Each ensemble member had the same weight. If I want to calculate the mean, for instance, of that ensemble, I just sum up all the ensemble members and divide by the total number, and then I get the mean, etc. Now here, you see that each ensemble member xi gets a weight wi, and the wi is different for each of these ensemble members. So we go from an unweighted ensemble or equal weight ensemble to a weighted ensemble. So the ensemble members, again, do not change. The data simulation doesn't change them. In the ensemble common filter, the ensemble members are moved around, are moved closer to the observations. But the particle filter, that doesn't happen. They don't move, but they get different weights. And the weights are these likelihoods, these normalized likelihoods. So what is this? Well, actually, it's embarrassingly simple. And suppose that the observation errors are Gaussian, and then this likelihood y given xi can be written as the exponent of 1/2, and then here this is just the Gaussian PDF, right? The observation minus the observation operator working on some member I. Here we have the error covariance, the inverse of the error covariance of the observations. And here we have the y minus h of xi again. And this is the term that you've seen in the variational methods all the time, and it comes from the likelihood, and the weights are just proportional to that. But this is really simple, because we only have to calculate this expression here. So I take my observation vector, I subtract the corresponding observations from ensemble member I, I multiply by this inverse, etc. And typically this matrix, this R matrix, is assumed to be diagonal, not always, but often it is. So this is extremely simple calculation. So you can just calculate this value, and that's all. So now we have these weights, and going back, we have solved the data simulation problem. And we don't have to do complicated matrix inversion or whatever. It's all very simple. Okay. So we're done. Can we now go home? Why did we learn about variation method? If there's this particle filters, fully nonlinear, right? No Gaussian assumption. Well, the issue is in these weights, with these weights. And I'll give you an example here. So on the horizontal axis, we have time, from 0 to 10 to 20. And we have observations every 10 time steps. So we start with these ensemble members, these small dots over here, and we propagate them forward in time from 0 to 10. And then we have the observation. And the observation likelihood is given by this gray PDF here. So I took the PDF and I rotated 90 degrees so you can see the PDF here. And then I do this weighting. Now, if you're close to the observation, your weights will be high. And if you're far away from the observation, so your weights will be low. And look at this, right? So clearly, when h of x is close to y, this is a small number. So I get the exponent of minus a small number. That will be close to 1, right? So it's relatively high. If, on the other hand, y and x are really different, and h of x are really different, then this will be a large number. So I take the exponent of minus a larger number, and that will be very, very close to 0. So we see that if you're far away from the observation, so the ensemble members that are over here or down here, they're far away from the observation, they get a weight very close to 0. And only these guys, these 4 guys in this example, get a weight that's non-zero, and the weight is proportional, again, to how close you are to the observations. And you see the size of the circle is proportional to the weight. Okay, so now I have my weighted ensemble. I propagate the ensemble forward to 2 times 20. Yeah, so I forecast the next day. Now you see that these ensembles up here and down there, they get even hammered more, right? Their weights will be even lower. And in this case, there's only sort of one ensemble member that gets a huge weight, and all the other ensemble members get a very low weight. Now, clearly, that's not a very healthy ensemble. Okay, if I calculate the mean, like I said earlier, it's a weighted mean, but the weights, if only one member has a large weight, then the mean is equal to that member. The variance is 0, the whole thing is degenerate, the whole thing collapses. It doesn't work. And so the particle filter in its naive form that I just mentioned really doesn't work. It's powerful, it's fully nonlinear, but it doesn't work. So what can we do? Well, we can do the following, right? So let's have a better look at what happens. So this is my prior PDF, and these are my ensemble members. I propagate them forward in time to the observation time. There are my ensemble members again. And the height of each bar is the weight of the particle. And during the propagation, the weight does not change. The weight only changes when we confront the members with the observation. So here's the likelihood. And the observed value will be somewhere at the top here. And this is this green line represents the errors in the observations. So now what I should do, I have to multiply these two PDFs. So I can multiply the delta functions with the green curve. So I do that, and this is what I get. So this is my posterior ensemble. And you see that the ensemble members over here, they got weight 0. So we can just forget them, right? Their weight is very, very, very small. It's only these, well, sort of 4 members that have a reasonable weight. But I started out with 10 ensemble members. I did the forecast, and then I did the data simulation. I have only sort of 4 members left. So that's not, of course, not very good. And I know that these members are not doing very well, and in the future, they're very unlikely to get closer to the observations again. So they're sort of lost. I don't want to propagate these guys forward in time again. Each of these, they have weight 0 anyway. Why should I put computational effort into that? But these guys, however, they're very good. So what can I do? Well, I can do something called resampling. So I make copies of the particles that are doing well, and I ignore the ones that are bad. And I do this in such a way that I start out with 10 ensemble members. I have again 10 ensemble members here. So I did throw away particles with very low weight, and I duplicated particles with very high weights. And then I gave them a small jitter, let's say, so that they're not exactly the same. And there they are. And then I can propagate this ensemble forward in time again. So this is a trick called resampling. And here you see it in action in a different way. Again, we start at time 0 with the particles. We propagate them forward to time 10. Then we do the weighting with the likelihoods. And then before we propagate these weighted particles, we're going to do the resampling. So again, the particles with high weights, they get a lot of copies. and the particles with lower weight get just 1 maybe, and particles with very low weight, they're just abandoned. And I do that such that I get well, the same number of particles that I had before. And in each of these guys, we still time 10, that's where the resampling happened, is now propagated forward to time 20. And again, I get my weighting and I can do my resampling, etc. So in principle, for many problems, this actually solves the issue. And so particle filters are used a lot in robotics, etc. So in all kinds of low dimensional systems, particle filters are sort of the method of choice. But if you go to high dimension, there's actually an issue. And the issue is that you can show that the number of particles that you need to avoid this degeneracy, this collapse on just one particle, is proportional to the exponent of something called the effective dimension squared of the system. And you can show or estimate that the effective dimension is related to the number of independent observations. So if you have, like in weather forecasting, you have maybe 1 million observations every 6 hours. And then this effective dimension is about 1 million. So we need the number of ensembles that we need, sort of like the exponent of 1 million squared. So that's just an astronomical number, right? We can never do this. So the problem in our field is that we have so many independent observations every time we do data simulation that you cannot use this particle filters. It will always be degenerate. So what would happen in this case is that immediately after at time 1, we would have, at time 10, one particle would have all the weight and all the other particles would have weight 0. So it's immediately degenerate. The first time we confront the particle filter with the observations, it's completely degenerate. So we really have to do something else. So this slide, I don't want to go into the details. You can look at it at home. It's one way to do this resampling. It's probably the most efficient way to do resampling, but I don't want to go into the detail of this scheme now. I want to move into an example. So this is an example of a highly nonlinear chaotic model. It's the Kuramoto-Shivasinski equation. I'm not going to give the equation, but it's sort of an advection anti-diffusion equation with a 4th order damping. If these words mean anything to you, and otherwise it's just chaotic. So this is an example of this evolution of the fields. So on the horizontal axis, we have the grid points. So we have 200 grid points here. And on the vertical axis, we have time. And you see what happens. You get these sort of worm-like features that interact with each other, that kill each other, and new ones are generated, etc. So you can look at you can generate a true field like the one over here. You say, so again, I'm doing these identical twin experiments that I'm sure you've seen before. So we generate a truth, and we generate observations from that truth, and then we're gonna do the data simulation. Now, if you do this with a particle filter, it's not gonna work because the system is way too high dimensional. But we can do this, run this model at any resolution. So we did here a run with only 10 grid points. So the dimension of the system is only 10, and we had 1,000 particles. And we had, observations, I think every 5 times that, but I'm not 100% sure. And here on the left, you can see the true field, the true evolution of the field. And on the right, we have 4 different data simulation methods. You can look at the particle filter without any resampling. So that is this figure on the upper middle here. And you see it doesn't look like the truth at all. And you see weird changes in the field, for instance, here, so discontinuities. But only without resampling, the particle filter just struggles and it just doesn't work. And it's not like the truth at all. If you use an ensemble common filter on this nonlinear system, it does reasonably well. But then after maybe 25 times that, it completely loses it. If you look at strong constraint 40 var, again, it's not doing very well. If however, you use a particle filter with resampling, it's called particle filter, sequential important resampling, that's a detail, but if you use this resampling trick that I mentioned on this low dimensional system, then it works pretty well. And you can recover this highly nonlinear evolution of this system. But if we're in high dimensions, what can we do? Well, three options have been explored in the field. And we can summarize them in 3 ways. One of is localization. Well, you're familiar with that because you've seen that in the ensemble common filter. That's a way to reduce the effective dimension of the system. Another way is to use proposal densities, and a third way, that's, like I said, the newer thing is to use these particle flows. So I'm going to go through these 3 different methods now. So let's first do localization. Now, like I said, localization, what you do, you can do it in different ways. But one of the ways is you just go grid point by grid point. And this is so-called observation space localization, right? So you go grid point by grid point, and you just look at, okay, at this grid point, how many observations? No, I'm just taking into account only those observations that are close to me, that are localized close to me. And so, for instance, I've taken a grid point here in the middle of this red area, and I only take observations into account in this red circle, within this red circle. And so observations from the Atlantic here, I don't take into account. It's only observations from the Pacific Ocean in this case. And I can do that, of course, for every grid point. And I can run the particle filter, and I have to do the weighting, and then I can do the resampling. And well, in this ocean case, the number of observations is relatively small. So you can actually do this, you can do the resampling, and you can get a new set of particles here, new set of equal weight particles in this domain, or at this grid point, I should say. And it will be similar in this whole domain. But now let's look at another domain over here, and we do the same. Now, as you can imagine, there will be different ensemble members will do good here than in this area. So that means that after resampling, the ensemble members that we keep in this area will be different from the ensemble members that we keep in this area. But now we have a problem, right? Because that means that let's suppose here we have an ensemble member 1 that is kept, and ensemble member 5 is being kicked out because its weight is too low. And for this area, it's the other way around. Ensemble member 1 has very low weight, so it's kicked out in the resampling, and ensemble member 5 has a high weight, so I keep it here. So how do I combine ensemble member 1 from this area with ensemble member 5 from this area? I have to somehow glue these two together, because I need to get one big ocean state again to propagate forward to the next observation time. And that's a tricky business, because how do I do that gluing? And well, people have come up with all kinds of fancy schemes, but it remains a tricky business, and it's difficult to make it stable. Yeah, it's not easy. And another maybe more pressing problem for the atmosphere, for weather forecasting, is that the number of observations in such localization area is typically still way too large. So if you would just use all the observations in that area, then again you would have this degeneracy. One particle gets all the weight and the others get zero weight. Just because we have so many observations in the atmosphere. And you could say, but then I can shrink my localization area just to make sure I only have 10 observations in. Well, but then you have a very small localization area, and you get all kinds of problems at the boundaries. You get balance problems, etc. So you can't do that. So what happens in practice is that people don't use the full weights. They cut off the weights. When the weights become too small, they cut them off, and they use all kinds of tricks to make this work, which essentially means that you throw away a lot of the information that is in the observation.
Peter,
yes.
The weight here is weighted computed by vertical filters for likelihood function, or is another way to compute this?
No. So the weights in the particle filter are just given by.
Oh yeah,
so
but I'm talking about the localization. So
yeah, but even if you do localization, it just means so I just restrict. I just take one grid point from X from this xi vector. I look at the observation that are close to that one grid points, like you do in the ensemble common filter, and then I calculate this thing. And for that local area, and as soon as you have let's say more than 10 independent observations, the weights will vary enormously, and there will be 1 or 2 members with a high weight, and all the others will have very low weight. And so this happens very, very quickly. It's extremely sensitive to the number of the number of observations. Does that make sense?
yes.
Okay.
Thank you.
Yeah, so in practice, we mix prior and posterior samples, we set minimum weights, we do all kinds of things, and then we can come up with scheme. If we tune this whole thing well, that work better than ensemble common filters, for instance, or even iterative ensemble common filters in nonlinear systems. But there's a lot of trickery needed. Another way is use proposal densities. And the thing is, there's some magic again in Bayes' theorem. So Bayes' theorem is, as we've seen it up to now, the P of X given Y, and then is equal to the likelihood, the prior, and then divide by P of Y. So that's what we've seen before. Now what I've done here on this slide, I've multiplied by some function Q, as another probability density function, Q, and I divided by the same probability density. So I've multiplied this whole Bayes' theorem by 1, Q divided by Q. And as long as Q is not 0, right, I can always do this. I don't want to divide by 0, so Q has to be non-zero. But if I do that, if I can find such a Q, then I can always do this. I can multiply by this Q. And I can choose any probability density that I want. Everything, anything. I can choose a probability density that depends on the observations, like I've done here. I can choose it. I can do that. You see, Bayes' theorem doesn't change. I just multiply and divide by the same probability density function. And why would I do that? Well, the thing now is, we can now, instead of drawing my particles from the prior, as I've done up to now, and then I get all this degeneracy, I can draw my particles from Q. And if I draw them from Q, so now Q becomes a sum of delta functions, and now the weights of these delta functions will be written down here in the second equation of this page. So it's the likelihood weights that we had before, but there's also these proposal density weights that is P of xi divided by Q of xi given by. And you see, again, if I write this Q as a sum of delta functions, this will be the weights. And so the weights are different, but still, typically this will be much better because this Q here, I can make this depend on observations somehow. And if I do that, that means that typically the particles that I draw from this density will be closer to the observations than the prior, because they've seen the observations here. So that means that the likelihoods of all these ensembles will be much closer to each other. They will be higher, but also closer to each other. So the likelihood weights will typically behave much better. Now, of course, we have this new part of the weights, but typically in practices, you can show that, also in theory, that this ratio, well, let's put it this way, that the whole weight, the weight, this whole thing is typically much better behaved than the standard particle filter. And this is an amazing trick, because what can we use for this QY? Well, it's something that already has seen the observations. So that means we can use a different data simulation method to come up with these Q samples. So I can run, for instance, I can run a 3D VAR on each ensemble member and use that as a proposal in the particle filter. Or I can run a 4D VAR on each ensemble member and use that as a proposal in the proposal density. Or I can use an LTTF or some iterative version of those. Or I can use something very simple. I can use some nudging on each ensemble member and use that as a member from this proposal density. Or I can use fancy things like synchronization, etc. And so if I go back again, this is a way this is a very natural way to combine data simulation methods. And the particle filter allows you to use other data simulation methods within the particle filter. And again, I keep on saying I draw particles from Q. What that means is I run, let's say I run a 3D var on each of my particles. So I have my prior particles. I propagate them forward to the observation time. And I have all my observations. The first thing I'm going to do is I run a 3D var on each of these particles. And because there are different starting points, the 3D vars will all be different. And these particles then are samples for my Q. And then I calculate this whole thing here to calculate the weights of each of these new samples, of each of these particles. So that's how this works. And again, it's a very natural way to combine data simulation methods. And so the hybrid data simulation method that people talked about before, you see there's a very general, this is a very general and mathematically exact way to combine data simulation methods. This has not been explored in full. There are many things that could be done. There's something called an optimal proposal density, but it turns out if you think about it, it's actually not optimal, at least not in the optimal in the way that we would like to have it. So there's still a lot of things that can be done. So if you're interested in this, then please jump in. What to do. But what I really like are these nonlinear data simulation, these particle flows. It's all nonlinear data simulation, what I've been talking about. But these particle flows, I think, are very elegant and very powerful. And I'll show you why I think that is the case. So bear with me for another 30 minutes for these particle flows. So this is the third and last part of the talk. So suppose we have a prior PDF denoted here by the blue dots and the blue contours. So this is my prior PDF at observation time. And I also can calculate, of course, in principle at least, the posterior PDF, right? And the difference between these two is the likelihood. So what I'm going to do is I'm going to move these states, these blue dots, this ensemble representation, this ensemble of states, I'm going to move them in state space from the prior to the posterior. And remember that this happens all at observation time. But what we're going to do is we're going to move these blue ones until they become samples from the posterior. And so they started out samples from the prior, and we're going to move them in state space such that they become samples from the posterior. And the only thing I'm doing, I have to come up with what is this flow field. I have to define how this particle, let's say this particle, this ensemble member in the prior, let's call it particle. This particle in the prior, how did that move from here to there? What was the evolution equation? But as soon as I have that evolution equation, I can just do this for each of these particles. And then you see there's no weighting. So this is not degenerate by construction. The only thing I have to do is to find these flow fields. So a way to move particles from the prior to the posterior. And remember again, I call it flow field and evolution, etc. But this is all happening at observation time, right? So it's actually an iterative scheme on each of the ensemble members, on each of the particles. These are the particles I'm gonna change to an iterative scheme such that they represent the posterior PDF. Okay, how do we do that? Well, we can write down an evolution equation. So X here is my state, and S is what I call pseudo time. So this is not real time. This is all happening at observation time. But it's just if you like, an iteration index. And f of s is this flow field. That is the flow field that I want to know. And And actually this whole method is a bit more general, because X can be a model state, but it can also be a whole model trajectory over a time window, right? So the formalism that I'm going to talk about is true both for a filter and a smoother. Okay, now remember what I said earlier about if I have an evolution equation for the state, I have an evolution equation for the PDF of the state. And that's what we're going to use. So we have this evolution equation. I do not know what this flow field is, but it doesn't matter. I can still just immediately write down the Langevin equation that gives me the evolution of the PDF. And in this case, because I do not have a random term here, this is the evolution of the PDF doesn't have this diffusion term. There's only an advection term, if you like. So this is the Liouville equation, which is the Fokker-Planck equation without the diffusion term. So this is the evolution of the equation of the PDF. And that we will use this evolution equation to come up to define this F. Because I know that for the PDF, I know I start as when S is 0, I'm at the prior PDF. And when S goes to infinity, I have to end up in the posterior PDF. Again, this is all happening at observation time, and S is pseudo time. So, okay, how do we do this? We still don't know how to find this F. Well, there are many ways. And one of the ways that we do this is we're going to minimize the distance between this intermediate probability density, P of S. Remember, when S is 0, this is the prior, and I'm going to change the prior, change this PDF slowly, iteratively, to become the posterior. So I'm going to minimize the distance between this PDF and the posterior. I'm just make sure that in every iteration, the distance decreases. And the distance measure I use, so that's to be the distance between two PDFs. So what I use is the so-called Kullback-Leitner divergence, or the relative entropy. And then, well, to solve this problem, we have to embed this flow field F in the reproducing kernel Hilbert space, but don't worry about it. It's in the end all very simple. So let's have a look at this distance. So this P of S, when S is 0, this is again is the prior. When S is non-zero, it's the intermediate PDF. It's the PDF of the ensemble when it iterates from prior to the posterior. And the Kullback-Leitner divergence is this thing over here. So P of S multiplied by the log of this ratio P of S and and the posterior. So first of all, you see that when P of S becomes closer and closer to the posterior, then this ratio is closer and closer to 1. Now the logarithm of 1 is of course 0. So when P of S is equal to the posterior, this distance is 0. And when it's not equal to the posterior, so P of S is not equal to the posterior, then the Kullback-Leitner divergence, so this distance between the two PDFs is larger than 1. Sorry, larger than 0. And again, we're going to minimize the distance. So how are we going to do this? Okay, well, let's take the time derivative of that distance. And of course, in pseudo time. So I just take the time derivative of that distance. And I'm just propagate the time derivative through this integral, and I shuffle a bit, and this is the expression that I get. There's no magic here. It's just standard mathematics of doing the derivative. And then, but the good thing about the expression, the middle equation over here, is that I have here the time derivative of my P of S. And I have an evolution of equation for that thing, remember? I can write it as this advection term. And we see now that this F of S is appearing. And that's nice, right? Because that's what we need. So we have this expression over here. And we can rewrite it a bit in this way. So I did a partial integration, and this is the expression that we get. So the P of S, F of S, and then this gradient of the log of the ratio of the probability densities. Okay, you might be lost now in the details. I'm going to confuse you even more. Because to come up with a scheme, and a scheme that is efficient, we're going to do something to this F. we're gonna embed this f in a reproducing kernel Hilbert space. And the only thing that means is that if I take this f and I multiply it with a kernel, and I take the inner product, well, more in general, I take the inner product of f and the kernel, then I get f back. So you see, I can reproduce f. I start with f and I do this with the kernel and I get f back. So that's why this is called the reproducing kernel. And Hilbert space only means that it's the space of differentiable functions. So we still don't know what to do, but we can use this expression here and we can plug it in this equation. And if we do that, we get that the rate of change of this distance between the probability densities becomes this expression over here. Where I had the inner product, I just took out the inner product out of the integral. I can just do it because the inner product is over the dot variable and not over x itself. Anyway, these are mathematical details. We can do this now, and of course, the rate of change of this distance I can write as the gradient of the inner product of the gradient of this distance. And f itself. So this expression, this integral here, I know that is equal to the gradient of the KL divergence. So how do I make sure that this becomes it decreases all the time? I have to make sure that this inner product is negative. So if I choose my f such that it is proportional to minus this gradient of the KL divergence, I get a negative number here. So that's what I'm doing. If I choose f in this way, in which the gradient of the Kullback-Leibniz is this integral over here, which I can rewrite in this way if I want, but that's not that important at the moment. If I choose f in this way, then I know that the distance between the PDFs decreases. And then finally, we say, well, this integral here is a complicated integral, but I know my probability density at every time. I have my ensemble of particles. So I can write this as a sum of delta functions, this P of S, as a sum of delta function at every pseudo time S. And then the integration over delta function, that was something nice. And indeed it is. So when I do that, then I get this expression over here. And this expression over here is all I need. And if you were lost in the mathematics earlier, don't worry about it. Essentially what we now have is an evolution equation that looks like this. We're going to move the particles in state space in this way, in which F is my flow field. And my flow field, I know what it is. I just had it on the previous page. So I just come up with an iterative scheme. So I discretize this evolution in pseudo time, and it gives me an iterative scheme. And so I start with a certain, yes.
The entropy here could be understood as an operator for select PDFs.
Well, I mean, the relative entropy can be defined for any PDF.
Yeah, it's I have a family of that I can fit in the with the observation, different PDFs fitting with the observation, and so I can use another criteria in order to select one.
Yeah. Okay. You mean I can use a different distance measure? Is that what you mean?
Yes. Yes.
Yeah.
So the metric that they're using help us to select the more appropriate PDF.
Yeah. But again, the methods on sich for the whole audience is completely general. I mean, make no assumption on the PDFs whatsoever. They can be anything. We just have come up with an iterative scheme that looks like this, and we just keep on iterating until the gradient of this Kullback-Leibniz is smaller than something. And this gradient of Kullback-Leibniz, right? It's so that's this flow field. You can see that as it's similar to the gradient of the cost function, right? One way to stop variational methods, to stop the iteration, say, okay, if the gradient of the cost function is smaller than 10 to the minus 17, then I stop, right? I'm just, so that's something that we're used to. But instead of a cost function, we have well, something slightly more general. Anyway, all these details, maybe too much. If we look at the flow fields, I just want to say a bit about how do we move these particles around? How does that happen? Well, we have the kernel here. And the kernel, so if I look at the flow field and for a certain particle x, I see that I get the kernel of that x with every other particle I, because we have the summation of I here. So this kernel here has to do with how it regulates the interaction between the particles. And what I'm doing it, I'm multiplying that kernel with the gradient of the log posterior of each particle. And this thing is the same as minus the gradient of the cost function. So this is the same term as you get in variational terms, in certain variational method. So this term here will push each of the particles towards the mode of the posterior PDF, towards the maximum, or if you like, to the minimum of the cost function. But it's an attracting term. All the particles move in the same direction. If there's one mode, if there are two modes, then they will split there. You get a split, but it's an attractive term. It attracts the particles to the modes. And of course, if we only have at this term here, the first part, then all the particles would in the end collapse on the modes and would be exactly the same, and we will just have a very expensive 3D bar. So that's not very useful. But we also have this term over here, the gradient of the kernel. And it turns out that's a repelling term. So if the particles become too close to each other, this term will push them away from each other. And it does it in such a way that in the end, if we just iterate this long enough, let's say 50 or 100 iterations, whatever, similar to what you do with variational method, then you need the particles cover the posterior PDF. And
I'm sorry. The B factor, it's a kind of a factor to do a better balance between these two terms.
Sorry, can you say it again? The B? Oh,
yeah,
the B here.
Because, yeah, you have B here.
So
yeah,
B,
and so
B is a, I didn't mention it also, it is a preconditioning matrix that just helps the minimization in the right direction. And so essentially what we're doing is some sort of gradient descent, and the B makes sure that we're doing something slightly smarter than just the straight gradient descent. But I must say there are other methods to do this, to implement this. So you can actually use a quasi-Newton or a Newton method on this to move the particles around. It is
okay. Thanks.
And nowadays people have come up with other methods than this. This is just the simplest, the vanilla one. And the thing I want to point out is that we get the same kind of forcing as you see in variational methods, but we have an ensemble, and it's a bit like an ensemble of 40 vars, like ISMWF is doing. Their ensemble of 40 vars. They call it the ensemble of data simulations. It's a slightly confusing wording, but they have this ensemble of 40 vars running, and each of these ensembles, each of these 40 vars is solved independent from any of the other ones. Now here is different. Here, at every iterations, the particles interact with each other. And that's the difference between the ensemble of 40 vars that ISMWF is running. It sort of mixes linear and nonlinear ideas. And here we don't do that. We make sure that we don't sneak in linearization or all that stuff. This is fully nonlinear. Okay. An example, right? Because you've been seeing equations and hear me talk for way too long. So let's give you a simple example with nice color plots. So this is a two-layer quasi-geostrophic model of the Antarctic circumpolar current. So there's the current around Antarctica. and the model has two layers. It uses the quasi-geostrophic assumption, so it's sort of simplified. It's not the full ocean model that you can do nowadays, but it's simplified. But still, it has about 500,000 grid points. It's a complicated system to solve. So we observe the upper layer variable once a day, every 5th grid point. That is the ocean, not the atmosphere, so everything is a bit slower. So we have about, 10,000 observations once a day. And to make it nicely nonlinear, we assume that we don't observe the variable itself, but we observe the square of the variable. So that suddenly makes it a highly nonlinear problem. Why highly nonlinear? Well, if you look at this is the surface layer, and you can look at the scale here. And so we change anyway. So the scale is here from 1.5 meter in the red area to -1 meter in the blue area. And so Antarctica will be south of this model. But you see that it straddles around 0, right? So of course, this observation operator doesn't see if the sea surface height in this case is positive or negative. The observation doesn't know. And so either the prior decides, or if the prior doesn't know either, then there are two solutions, or the posterior will be bimodal. So that's why I did choose this, because to see if this particle flow field can actually do this. So we use 50 particles. We use no localization because we don't need localization. Well, perhaps I should say we use some sort of localization in this precondition matrix. This matrix is based on the ensemble, and it's so we use some quick and dirty localization, if you like, there. But that's just for the precondition matrix. Apart from that, we don't use any localization. And then we run this, and just give you an example. In the upper figure here, this is the prior mean. The prior mean. And you see the meandering and all the eddies and all that stuff. In the middle, we have the true fields from which we generate the observations. And in the lower part, we have the posterior mean. And you see that the posterior is much closer to the truth than the prior. For instance, here there's an eddy being shed off. That's not that far in the prior, and also in this area, you see large differences. Find the 7 differences. That's the posterior is the data simulation is doing the right thing. That's what I want to say. And that was the upper layer and the lower layer. This layer is not observed, but again, the posterior is much closer to the true field, showing you that even if the unobserved variables are also updated, like in any sophisticated data simulation scheme.
Peter.
Yes.
Peter, 10 minutes, please.
Sorry?
10 minutes.
10 minutes. Okay,
so
sorry.
You can go. Yeah.
Yep.
All right.
Absolutely. Sorry. Thank you. So I just want to show you this one. This is an example. This somewhere during the data simulation in one of the grid points. What I'm showing you is the stream function value in that grid point. So this is, like I said, an observed grid point. The blue bars are the ensemble members, and I think I did 100 ensemble members here. Yeah, must be. So this is an experiment, so not with the 50 ensemble members that I showed earlier. This is a different experiment just to demonstrate this specific point. Yeah, so blue is about 100 ensemble members. The prior, and so the prior straddles the positive and the negative value. Now the red bar is the observation. Now, of course, we only have one observation, but we observe the stream function value squared. With me. So that means that in state space, so in observation space, there's of course one observation, but in state space, there's sort of, you can think about it, there's sort of two observations, right? A positive one and a negative one, and yeah, they're both as valid. And indeed, my posterior PDF is a bimodal distribution that captures that solution. It doesn't choose one of them. It says, okay, I just don't know. So I I produce this bimodal distribution. And this is not the only time this happens. Another thing that I think is interesting, what can happen, is that the prior can be completely off. And of course, we don't know exactly what the distribution of this prior is. We have a small number of ensemble members, and this is again from 50 ensemble members. The observations are over here, close to 0. So what the method can do, it can correct for that bias and pull the whole ensemble on the in the right part of state space, given by the observation in this case. So let me see. I just want to show you one example, and this is the Lawrence 96 model, 1000-dimensional. We have an assimilation window of 10 time steps, and we observe the absolute value of the state. So again, it's a nonlinear observation operator. So we would expect to see something interesting. Show the result of 50 particles. And this is an example of a smoother. The previous one was a filter. This was a smoother over these 10 time steps. So the plot on the left, let's start there. So this is at the end of the window where we have the observation. And we have one observation. Sorry, we observe part of the system at the end of the window. Does it say how many? Every other grid point. Okay. And so we observe 500 observations in the 1000-dimensional system at the end of the window. So here you see that the particle flow filter indeed splits. You get a bimodal PDF because we observe the absolute value of the state, and it can be positive or negative. So this is what you want the system to do. The particle flow is doing the right thing. And again, there's no localization, right? Is it just how many ensemble members did I use? No. 50 particles. Okay, now this is the same grid point, but now at the beginning of the time window, the start of the time window. So again, this is the analysis. This is what the ensemble. Oh, I should say here. What we see on the horizontal axis is iteration number. So we see how the particles are moved in state space towards their final position. And again, this is all happening at observation time. So this is at grid point 900, at the end of the time window, we are looking at how the particles are moving in that grid point. And this is what happened. If I look at the same grid point at the beginning of the window, I see there's no clear separation, right? This again showing that the system is nonlinear, right? The red lines here correspond to the red lines here, and there's no clear. We can't see at the beginning of the window where these particles will end up. Anyway, I compare this with the ensemble of 40 var that ESMWF is running. Now, sometimes the ensemble of 40 vars does really well. This is an example where it does not. And that's because it's sort of this mixture of linear and nonlinear ideas. And for instance, when it should produce this bimodal PDF that we find with the particle flow smoother, the ensemble of 40 var gives us a unimodal PDF. At the end of the window, at the start of the window, it does the right thing. At the end of the window, it gives you the wrong thing. Okay, so let's summarize then. So nonlinear data simulation is slowly becoming mainstream. We have all these iterative ensemble common filter method, etc. We have ensembles of 40 var. But there's also now the particle filters for low dimensional systems, and the particle flow filters and smoothers for these very high dimensional systems. And so we can do that now. And we are implementing them in Dart and in JEDI, these data simulation frameworks. And there's really a need for many more scientists to work in this field. And then I'd like to end with advertising this free open access book at this DOE that recently came out. Okay, thank you so much. That's all I had.
Okay, thank you very much, Peter, for your talk this way. We're starting with a very didactic, and we can follow all your ideas about particle filter, and then we introduce this modern, advanced schemes based on in flow particle filter. Thank you. I appreciate a lot for your presentation here. And thanks also for accepting our invitation to be here. We have one questions up to now in the chat. I did it. I put it.
Okay. Yeah. So the question is, if the true PDF is a Gaussian distribution, considering the prior PDF is a Gaussian.
No, the prior Cauchy.
No, sorry. The true
prior
PDF,
PDF is no. The true PDF is Cauchy. The prior is Gaussian,
and the
likelihood function is Gaussian too.
Okay. So then, of course, when my prior is Gaussian and likelihood is Gaussian, then Bayes' theorem tells me that I get a Gaussian posterior PDF. So that's what this particle flow filter will converge to. So I'm not sure what you mean with the true PDF, right? So the PDF, of course, is always a representation of what we know about the system.
I mean, true PDF means imagine that you are in a wall, that the random variables, well, the random variables have the distributions like a Cauchy one.
Mm-hmm.
Okay, and so in this wall, the random variable, like our atmospheric dynamics, follow the Cauchy distribution.
Mm-hmm. Oh,
that's it. And so in this wall, I try to apply the particle filter using these considerations. The prior is considered Gaussian, and the likelihood function is considered Gaussian. And then the question is, can I converge using this strategy for particle filters to get the Cauchy distribution?
Okay, so you're saying that the observations are
the Cauchy
from the
Cauchy plus one additional noise.
Okay, okay. So this is a situation where the prior and the truth are not drawn from the same distribution, right? So that is okay. Yeah. So it's interesting. The thing is that of course. When you draw your samples from the prior, they will be Gaussian distributed, like you say. But of course, you only have samples, right? You maybe have 100 samples. So yeah, it's actually. Yeah, how does this work? No, I think Bayes' theorem tells us that this is not going to work, and so
yeah, because
what's going wrong here?
By the way, the Cauchy distribution, there is no variance.
No, exactly, right. It's
right.
Yeah.
Yes.
Very heavy tail.
Long tail.
Yeah.
Yeah, it's never go to zero.
Yeah, it doesn't even have a mean, right?
Right. Yes.
In
additionally, we have this. Yeah.
This is no variance.
I mean, all statistical moments are not defined.
But yeah, so I think this is this is an issue in the sense that Bayes, yeah, our prior knowledge is just normal and it's a normal distribution. And if the observation errors are just Gaussian distributed, then we will get a Gaussian out, and that's what Bayes' theorem will tell us. And the particle flow and any data simulation measure will try to mimic Bayes' theorem. So I don't think we can ever get that. But there's no information anywhere that there's an underlying Gaussian distribution. Of course, if you run this system over time, then the system will realize that, oh, wait a minute, I'm assuming things are Gaussian, but they are not. Because the observations are in weird places all the time. And then yeah, so definitely the particle flow filters will be able to adapt to that different distribution. But it's over time. It's somehow the information that the two distribution is Gaussian has to be brought into the system. Otherwise, you can't know.
Okay, maybe it's something that you need to investigate and to do some numerical example, what's going on in this situation.
Yeah.
just in case, right?
Yeah. Yeah.
I'm wondering if different strategies for particle filter good, because statisticians, they use different likelihood function depending on the application that they are interested in.
Well, but yeah, but the likelihood function in the end should represent what the errors in the observations are. And okay, that's where this.
Okay,
yeah.
Just one issue to think, or maybe to do some numerical experimentation, or.
Yeah, so I think you're right. It should come in through the likelihood that you at some point the likelihood. No, but if you assume anyway, okay.
Yeah, but
it's not the right time.
There's one statistician applying for in economy, and then he moves to apply to statistical mechanics, and they are using, I mean, using different operators for likelihood function. Mm-hmm. So for different problems, he applies different mm-hmm. likelihood functions. So
yeah.
This is another thing to think about.
Yeah.
Maybe. All right.
Yeah. Sort of the hyper parameters in the system, right? Yeah. Yes. So there's one thing I'd like to say to the students. I mean, perhaps this looks already rather mathematical and complicated. It's in essence what you're doing is you're with these methods is you just where is it? You're just solving. If you do this particle flow filters, you're solving a set of 3D vars, and the only mm-hmm. thing you have to make sure of is that these 3D vars solutions, or during the iteration, they communicate with each other through the kernel. So you just have to calculate this kernel. Typically, the kernel that we use is a Gaussian. So we just calculate this Gaussian, and then we multiply by the gradient, which essentially is minus the gradient of the cost function, and you calculate the gradient of this kernel. It's there's nothing fancy in the end in the methodology. It's easy to implement, and yeah, it's. I'm just saying, if you get lost in the math, it doesn't matter. You can still use these methods, and then later on realize what's going on under the hood. But it's something very similar to what we've been doing before.
Yeah, that's a good point that you are pointing out here. There is no difficulty in terms of computational implementation. Yeah, that's a good point, Peter. Someone else want to ask something or comment for Peter? If not, I'm going to thank you again, Peter. Mm-hmm. And that's very, very interesting presentation here. And you have a break.